Hello and welcome to another LTspice tutorial video. This time I will be explaining the implementation and uses of the .step and .param spice directives. Let's start simple, the .param directive. Basically, just like the help file tells us, it's like defining a variable or constant in a computer program. It works by generating a user-defined value and using it inside the circuit as a component parameter. As we can see, a bunch of mathematical functions can be used together with it, so it's not as simple as x equals 1, it can become much more complicated, like x equals the absolute value of 1, which is 1. An important thing to remember about the parameter is that it's a constant throughout the simulation, meaning it can only take one value for a single run of a simulation. So, what is this useful for? Well, one use is attributing the same value to multiple components. Let's say you're working on a multi-stage passive filter, and you want all components to have the same value. Here we can see a third order low pass filter, and we will give parameter values to our resistor, let's say 1 kilo ohm, and another parameter to our capacitor, let's say 10 nanofarad. And now we can tell each of our resistors that their value should be the value of the resistor parameter. And the capacitor will be the capacitor parameter. Let's just make everything nice and tidy. And we can perform simple AC simulation. Of course, you need to make sure that the same name is in the parameter store and in the definition. And this time we will see how each of the stages of our filter is influencing our output signal. Maybe we didn't make the best simulation, and we can see each stage having a greater impact on our input signal. Now if I want to change the parameters, I can simply change all three capacitors at the same time using our parameter directive, and the response of the circuit changes. Another example is performing mathematical operations, once with a circuit on a certain electrical parameter and once with a formula, and then comparing the two to see if your circuit actually works as expected. For this we can make a simple resistor divider. If we put two identical value resistors, we expect the output voltage to be half that of the input voltage. Now we can check this once by simulation. Let's say we have an input voltage parameter. We have our output voltage actual value. And we have as a parameter the theoretical output, which is equal to the input voltage divided by 2. This way we introduced a formula into our parameter definition. Now if we run the simulation, we will run a transient simulation. We see our input voltage at exactly 1 volt, our output voltage, and we can't see our theoretical output voltage because it has not been assigned to anything yet. So we will create another voltage source and assign this theoretical output as a voltage parameter to this secondary source. Now we see our output voltage, the actual output voltage, and we see our theoretical output voltage, which is exactly the same as our output voltage. Next, the .step directive. This is a function that works by giving multiple values to parameters and performing simulations with each of them in the same run. So in each simulation you will have a different parameter value. You can give values to user-given parameters, like our previous input voltage, to component parameters, like a transistor's forward early voltage something, or to the simulation temperature. Also, the given values can be in the form of a list, or it can be defined as an interval with a number of steps incremented in a logarithmic fashion, or with an incrementation interval. It's up to you how you want to input your data. Okay, so let's see this thing in action. We can check what happens when we build a voltage divider with multiple resistor values. In this example, we will call our first resistor the upper, and then the other resistor the lower. We can have two separate step directives for each of our parameters. First, let's say we want a list of values, 1 kilo ohm, 10 kilo ohms, 100 kilo ohms, and then our lower resistor, we will define it differently. Let's say we want values between 1 kilo ohm up to 10 kilo ohms in 1 kilo ohm steps. This way we have an incrementation interval. Now, if we perform a simulation, we will see that we have very large number of output values. Why are there so many? Well, the simulation took all the possible values from one parameter, so our free values in the upper list, and then all the possible values for our other parameter. So for our lower resistor, we had between 1 and 10 kilo ohms in 1 kilo ohm steps, 10 values. So in total, we should have 30 simulation runs. This number came out by multiplying all possible combinations of parameters. Now we can see each of our results in our simulation window. We can cycle through them with the arrow keys. By going up, we will go through the various simulations. And then when we find one that we actually want to study, we can simply right click on it, and then the simulation will tell us what the values for the two parameters were and which run was this combination obtained in. So in our 30th run, the upper resistor had 100 kilo ohms and our lower resistor had 10 kilo ohms. Also in this run, the output voltage was 90.9 millivolts. Although this seems like a simple example, the power of the step and param directives becomes obvious when working with multiple parameters at the same time in a more complicated circuit. For example, you can see in my previous video how I implemented an audio filter using these two statements. Hope you got some useful information out of this. Let me know what you think about this series in the comments, and see you next time. Bye bye!